So now we identified the system. The next part of your project is to design a controller. In an open loop system, you can only just give a control value and system responds by itself. In a closed loop, you can set a temperature and ask the system to go to that temperature. To do a control like that, we have so many control algorithms we can use, and the most widely used algorithm is PID controller. So in this, we are going to find out the PID values for our system. So this is where we ended up last time. We found the system equations. Next thing you have to run is this simulate heaters program. This is already written for you. You don't have to change anything here. Once you run the first program, this station data.mat file is created, and that's all what it needs for this second program. Before that, let me show you how we are going to tune the system to find the PID values. So if you check, this is a closed loop system diagram C4.1, and C4.2 shows a response of a system to a proportional controller. So if you use a small value for this proportional controller, this will have a high steady state error. Whenever you start increasing this Kp proportional controller value, system starts to oscillate. Whenever system has the first oscillation, the time between the first two peaks, this is known as the oscillation time period Pt, and whatever Kp value goes that, it is known as ultimate K or Ku. So let me go to the next page. So here you can see it is named Ku, that is the ultimate gain which produced this oscillation whenever you started increasing Kp. Then Pt is our oscillation time between two peaks. It should be in seconds. So whenever you design a proportional controller, you only need a Kp value or proportional gain value, and that you can select as half times Ku. Then you don't have a Ti or Td. Then whenever you design a Pi controller, you need a P value and an integral value. So for P value, you can use 0.45 times the Ku value you find out which created the oscillation. And the next thing you have to find is the I value, Ki value, that is the integral gain value. So if you check equation 4.3, this is the Pi controller, and Ki is equal to 1.2 times Kp by Pt. So this is the Ki value. And finally, for PID controller, you need three values: Kp value, Ki value, and Kd value. So in equation C 4.4, you can see Kp is 0.6 times Ku, which we found here. What K caused this, Kp caused this oscillation. And Ki is 2 times this Kp divided by Pt. Pt is the oscillation time. And Kd derivative gain is 0.125 times Kp into Pt. All values we know. This is another representation of that table, but all you have to notice is this equation 4.2. This is proportional gain, proportional controller. 4.3, which is Pi controller, and 4.4, which is PID controller. So let's go back to our program and see how we can do that. So I'm going to run this simulate heaters. So it's going to take a small time. So it simulated the data. So if you go to this open loop data, this was 3 system response. So that solid lines, that's what came from our text files, and dotted lines is the fitted line. So we used a least square to fit the system. So this was the system response with that system equation. There is a small difference between actual system and simulated system. That's expected because we are approximating. So these are 3 responses. So make sure to save this figure and use in your report. So that's about this open loop system. System rises from a lower temperature for the control and stabilizes to a steady state value. I'm closing this. And this one is the PID simulation we can use. So first what you have to do is you have to find an ultimate gain. For that, as I mentioned, you have to increase this Kp. So if I select a value of 0.001 and click simulate, you can see the system is responding, but there is a high steady state error. Now if I increase this to 0.01, you can see again it increased, but there is steady state error. I can again increase this to 0.1. You can see system is having oscillation. So what you have to do, and if I change this to a higher value, say 1.0, you can see it's becoming an oscillatory system. So in the first part of the program, you have to use a smaller Kp value, keep on increase, then whenever this has one oscillation, find the time between that oscillation, and that is your Pt, and whatever Kp cause that, it is known as Ku. So note down your Kp and Ku value somewhere. Kp is equal to, note down it like this, Ku is equal to, note it down like this, because whatever Kp caused that first oscillation. Then what was your Pt, oscillation time. So note down those two values. Once you know these two values, for UP controller or proportional controller, you can find a P value. So for that, you can make use of equation 4.2 to find Kp. And for PI controller, you can use C4.3. What should be the Kp value and what should be the Ki value. And you can use 4.4 to find PID gains. So these are the PID gains. So here I fill this Kp value, fill here Kp value, Ki value, and nothing. And for PID you will have Kp value, Ki value, and Kd value. So I will suggest you to make a table like this, which shows what is the proportional controller gain to be used, what is the proportional integral controller gain to be used, and PID controller gains to be used. So that's how you have to work. Once you have this value, come back here and input those values here, Kp, Ki, and Kd. So if Ki is not there, put 0. If you know, for PI controller, put some value. For PID, you will have D value also. Then click simulate to see what happens to the system. And if you check here, you can see what is the overshoot, what is the set temperature. Right now, the set temperature, initial temperature is 20. That is our uh, ambient air temperature we are considering. Set temperature is 300. You can change this to 200 also, and you can try to simulate. So this will simulate what happens when you set the temperature to 200. You can see here dt is the difference between time, tf is the simulation time, u minimum and u maximum. These are our limit. We can only give a maximum input of 4, and the input minimum should be 0. So input varies between 0 and 4. So that's all about the simulation. This might be little confusing at first time. Just call me if you have any doubt. I will explain to you. So what we are doing here is simulate the system and see what is the system response. Once you know the simulator response, use this in the actual system. Get these values, use the lab view, input those values to the lab view, and see how the actual system responds. As always, there will be small difference, and whatever difference you see, that is what you have to explain in your report. Okay, thank you.